You are all familiar with Moore and Mealy FSM, so I will give just a brief intro about Moore and Mealy FSMs. So, in case of Mealy FSMs, the output will depend on input as well as present state. Whereas in case of Moore FSM, the output is dependent only on the output will depend upon the present state. So in case of Mealy FSM, the output will depend upon the input and present state, whereas in case of Moore FSM, the output will depend upon only on the present state. So this is the basic difference between the Mealy FSM and Moore FSM. Is this clear? So coming to the state diagram representation. So for example, if there is a reset state, we will go to some state called S naught, and we have say three states like this S2. So if reset, we will go to S naught state and output is 0, and if the input is 1, the output is 0, and we will go to the S1 state, and if the input is 0, output is 0, and we will go to the S2 state, and if S2 in the S2 state, if the output is 0, then sorry, if the input is 0, then output is 1. This is a example, this is just an example to show what's happening. And in S naught state, let's say if the input is 0, output is 0, and the state is S naught. And here if the input is 1, output is 0, and here if the input is 1, output is 0. So this is just an example of Mealy FSM. So in case of Mealy FSM, you can see that the output is dependent upon the input. So output is dependent upon the input and present state. This is clear, right? Am I audible?
Yes.
Yeah. So this is Mealy FSM. So this is how we draw the state diagram for Mealy FSM. But we generally don't prefer Mealy FSMs because there is more noise involved because of involvement of input. So output is changing because of the input. So if there is any noise in the input, then the output we will get the noise. So if there is any input noise, then it will be affected at the output also. So generally we don't prefer Mealy FSM. So we go to Moore FSMs, because here the output is not dependent upon the input, it is only dependent upon the present state, upon the present state. So same scenario, when reset, we should go to S naught, and here the output is 0, and if 1, we go to S1 state, output is 0, and if it is 0, same state, output is 0, and if it is 1, output is 0, and in S1 1 0. So it should, so in S1 if the input is 1, it should go the output will be 0. So this is the diagram, and if 0, then it will go to S2 state, output is 0, and in S2 if the input is 1, it will stay in the same state,
We are looking for 101 that sequence.
Yeah, some random sequence I have taken, just like that.
Okay.
Yeah,
In melee 1 by 0, we provide like 1 by 0.
yeah.
So one is the
One is the input.
one one is the input, and by 0 is the output.
Numerator is the input, and denominator is the output. This is to show that output is depending upon the input. So this is a representation. We show that our output is depending upon the input. Whereas in case of Moore FSMs, the output is not depending upon any input. It is only depending upon the state. Here, that's why we have written the output below the state, not below the input. So this is how we can identify whether the state diagram given is a Moore FSM or Mealy FSM. And from S2, if the input is 0, it will go to S0 state. So basically we are detecting the sequence 101, sorry, 100, 10 and 0. So this, sorry, here we will get one more state. It will not go to uh, this. So it will go to, if the input is 0, it will go to S3 state and the output is 1. So in Moore FSM, we will have one more state. So basically, I have taken a just random sequence 100, 100. So we can see in Moore FSM, we have more number of states compared to Mealy FSM for the same sequence. In Mealy, we have only 3, whereas in case of Moore, we have 4. Is this clear?
Yes, for me.
So this is the state diagram of Moore and Mealy FSMs. So in this session, I'm going to discuss about the coding of Moore FSMs, because we will mainly use Moore FSMs only in majority of the cases, because the output is not depending upon the input, so there is less prone of noises. So in this FSMs, we have two parameters. One is present state, that is the present state where we are in, that is the current state, whether it is S0 or S1 or S2 or S3. And we have one more called next state. This next state comes when if there is a particular input, say input is equal to 0, then where we should go, that is told by or given by next state. Or the input is 1, then where we should go, or where which state we should go, that is given by next state. So basically next state logic tells us to which state we should go when there is a particular input. So when there is a particular input, then which state we should go is given by next state logic, and present state is the state which we are currently in. Is this clear? Is the present state and next state logic clear?
Present state is like the initial state it is.
No, no, not the initial state. So present state is the current state, where in which state we are in. Next state is a future state. So if a particular input is given, then where in which state should we go? So that is given by next state.
Yes, exactly.
Is it clear?
Yes, clear, sir.
So if the input is 100, so we will see the coding for this. So the diagram is given here. So we will code for Moore. So first we will declare a module, that is same module name, and inputs and outputs we will declare. And here your wish, if you can declare a parameters or not, your wish, but normally we will declare some parameter, say idle state is equal to 2 tick binary 00. Basically for writing the states, we will declare some parameters. Instead of writing the hard coded numbers, we will declare the names for each number or state. and parameter s1 is equal to 2 tick binary 01, and parameter same s2 is equal to 2 tick binary 10, and parameter s3 is equal to 2 tick binary 11. So this is how we will declare the parameters. So this is each individual state. Now we will declare two registers. Since the parameter width is 2 bits, so we will declare present state and next state of 2 bits. One is present state and another is next state. So these are the two states which we are going to use. So the present state logic which we are going to write is a sequential logic, and next state logic which we are going to write is a combinational logic. So the logic which we are writing for present state, that is which state we are currently in, to know that which we are writing, it is in a sequential logic. And the next state logic, that is if a particular input is given, then to which state we should go, that is given by next state, that is we will write in combinational logic. Normally if we think like this, so if this is a design and these are some of the inputs to our design, and this is our output. So our output is state, future state. It is depending upon the input. So output is depending upon the input, which is nothing but a combinational logic. So this is how we can analyze it. Is this clear? So that's why we are writing next state logic in combinational logic. Is this clear? I will write the code, it will be more clear. So present state logic, it will be in a sequential logic. So for sequential logic, we will include the clock, that is passage of clock, begin. So first we will include the reset condition. Then since we are writing the present state logic, present state is equal to idle. I will use a non-blocking statement since it is a sequential block. Else present state will be equal to next state. So if reset is low, then next state will be assigned to present state at the passage of clock. Is the present state logic clear? What we are going to do?
Next state.
Yeah. Next. We are writing, next we are seeing about next state logic. So it is a combinational logic. So I will use asterisk, always at the rate asterisk, and I will use a case present state. So if it is ideal state, then begin, I should do some operations. Say here in S0, if my input is 1, so if my input is 1, I should go to S1 state. So I'll write here case present state begin if 1, sorry, I will take this as my input, some register input reg in, like this. I will take that. So if in is equal to 1, or I can write simply if in, then next underscore state should be S1, else next underscore state should be so Yeah, it should be idle. So in idle state, if input is 1, then I should go to S1, else next state should be the same state. So here next state logic is is deciding the next state, that is upcoming state. So according to the input it is deciding, and it will be stored into the next state, and at the passage of clock that next state will be assigned to present state, and we will be in that current state. So the FSM will be in the current state. So what happens here is, when reset, our present state will be idle like this. And here parallelly with this always block, the next state logic block will also run. So this is the next state logic block, next state logic block. So parallelly with the present state logic block, our next state logic block will also start. So if reset, we will get into idle state. So at the same time, here the case statement will also begin. So if we are in idle state, it will start to analyze, it will start this block. And if the input is given to this block, so if the input is equal to 1, then what it will do, next state is equal to S1, so next state will store the value of S1. So whenever a positive edge of the clock occurs, then the present state will be equal to S1. Then our current state here, it will be equal to S1 whenever there is an input 1. Similarly, when and what condition we have given, next state is equal to S1. So our present state now it will be in the S1. And now we should write another case, that is S1. So if we are in S1, what we should do, we should write here, begin if not of in1, that is in1 is equal to 0, in1 is equal to 0, then begin next underscore state should be equal to S2, else next underscore state should be equal to S1. So what happens if my input is equal to 0, then my next state will store the value of S2. And when the positive edge of the clock occurs, then that next state value will be stored in my present state. Now present state will be equal to S2, so I will go to my S2 state at the positive edge of the clock, like this, if it is equal to 0. Is this clear? Is this process clear? If you are having any doubt, you can ask me. And similarly, if it is not equal to 0, then next state will be equal to S1 only. So then now next state value will be equal to S1 when in1 is equal to 1. So the next state will hold the value of S1, and when the passage of the clock occurs, then what happens, then present state will hold the value of S1 only. That is, we will be in the S1 state only, we will not go to S2 state. So this is what happening. And finally we can write the output logic, that is or else we can mention here only. So if in in1 is equal to 1, next state is equal to S1, and we can declare one output variable, say m. So m is my output variable, m is equal to 0. M will be equal to 0 if in1 is equal to 1 and next state is equal to S1, else next state is equal to idle. Here also m will be equal to 0. Like this I can write the output, what should be my output. Is this clear what I am doing? So this is the Verilog coding. So this is how we will do the Verilog coding for FSMs if there is any FSM included. So that's all for today's session. So if you are having any doubts, you can ask me, or else we can end this session.